So hey guys, my name is Cedar Shen. I am a product marketing manager at Seller Data, and I'm also a contributor to the StarRocks project. Today our topic is around data lakehouse. 5 brilliant data lakehouse architectures that we can learn about, right? So here, first, let's talk about the agenda first. Our topic is on the 5 Lakehouse architectures, but they have a lot of things in common, right? Including the pain points of their previous solution and how they overcome their pain points by either transforming into a lakehouse architecture or optimizing their architecture, right? There are a lot of similarities and a lot of common things. So I want to extract all of the pain points and the solutions, talk about them first, so we don't have to repeat ourselves when we talk about the case studies, right? The focus on the value, the important things. So first, I'm going to briefly talk about what is data lakehouse and the benefits of data lakehouse. And then I'll talk about the one thing that can easily break all of the data lakehouse promises, right? Slow queries. And then we're going to talk about the challenges that comes with data lakehouse queries. Challenges come from optimizing the queries, right? How is it different from a data warehouse, right? And then we're going to talk about the solution to the performance problem, right? What vendors in the industry is doing to optimize the performance, so you can get data warehouse like performance directly on the data lakehouse, right? And then we're going to go into the 5 lakehouse architectures, lakehouse case studies from industry leaders, right? So first, what is data lakehouse, right? We all know what a data lake is, right? It's a place for you to dump all of your data, structured, unstructured, semi-structured, in open formats, open and standardized formats, right? And data format, or table format vendors such as Delta Lake, Apache Iceberg, and Apache Hudi has been adding data warehouse-like features to data lake, right? Essentially making them lake houses. On the right, you can see transactions, compactions, and time travel, those advanced data warehouse features, right? So all in all, data lake house is basically a combination of the features of a data warehouse plus the open and standardized storage engine, right? As open and standardized table formats, metadata, like the 3 I've mentioned above, Delta Lake, Iceberg, and Hudi, and also file formats, right? Open and standardized file format, such as Parquet, right? And an immediate benefit of using open formats, open standardized formats, is that you can unify all of your workload on a single source of truth data, a single copy of the data on the data lake house, right? Let's say, for example, you're using a proprietary data warehouse, right? The amount of workload you can do on a proprietary data warehouse is limited by the capability of your data warehouse and probably a few connectors, other applications that can read the proprietary format of your data warehouse, but nowhere near, the number of applications you're going to need, right? But with open formats, you can easily connect to all kinds of applications, not only processing engines, query engines, machine learning applications, or AI, deep learning, frameworks, right? And so you can unify all of your workloads on a single source of truth data. So the benefit is enormous from this, right? So you can get easier data governance because you're only managing one copy of the data, right? You don't have to synchronize like multiple copies of the same data that's scattered around in multiple systems, right? It simplifies your architecture because there's only one storage you need to worry about optimizing and worry about being stable, right? And overall, it's very cost effective because you're not copying your data, you're only storing one copy. And also from simplifying the architecture, right? It's a lot less stress on your labor, right? And this is all good, right? So we must be running all of our workloads on the Lakehouse directly, right? But the reality is no, and users are still copying their data out of their data lake house purely for query acceleration reasons. The reason of that is existing data lake query engines are not performant enough for the insanely demanding workloads that we're trying to throw at it, right? Low latency, high concurrency workloads. They're either not optimized for high concurrency, low latency workloads. Instead, they're optimized for batch, right? They're not optimized for performance, but they're optimized for long running jobs that runs for 4 or 5 hours or even days, right? Or they're still on older technologies. They're not taking advantage of all of the crazy optimizations we can do to a query engine today, right? So they're not able to handle the workloads, customer facing, high demanding, low latency, high concurrency workloads. So as a workaround, data lakehouse users are often forced to still move their workloads and the data to a high performance data warehouse purely for query acceleration reasons, right? And this does solve the problem, the performance problem, but it brings a whole other set of challenges. So first is maintaining the data warehouse. It doesn't matter how simple the data warehouse is, how light it is. It's still infra level software with state, right? It stores data. So maintaining that is a big hassle, no matter how you put it. And also it comes the cost of the data ingestion pipeline. Data ingestion is basically writing your data files to the proprietary file format and table metadata format that's required by the data warehouse, right? And that process can be very resource intensive and also labor intensive to maintain, right? And also you have to kind of match the schema, your data lake and your data warehouse, match the data type and match the SQL, right? And also you have to design a whole new set of schema, indexes, a lot of things, right, in the data warehouse that can be very labor intensive. And also you're copying your data out of the data lake. I think this is the most important thing, right? You're copying your data out of the data lake. So you basically break the promise of a data lake house, right? So you have to like maintain multiple copies of the same data, trying to keep them in sync. That's a huge data governance nightmare, right? That you have to deal with. All of this just for good performance. And this is a big problem, right? The reason for this is that I'm going to talk about this in the next session. So the challenges that comes with accelerating data lake house queries, right? So the main challenge, the biggest cost of data lake query is actually fetching the data, metadata, from your external data lake and data lake house storage, right? So first is the network overhead that comes with it, right? It has to go through network, and that does not only make the processes slow, but it also affects query execution as well, because any like query engine that does join or high cardinality aggregation, they do data shuffling at query execution, and that process needs network I/O. If you take all of the network I/O, like reading external data, that can really hammer the performance of your query engine and makes it insanely slow, right? And also the slow and unpredictable performance of data lakes. Data lake, you're not the only one that's using it, right? And that can, the latency and the I/O can be very unstable. And also, data lakes are on slower storage devices, HDFS or cloud object storage. Let's take S3 as an example, right? Latency of S3, AWS S3, can be more than 100 milliseconds, but on an NVMe SSD you can get that sub 10 milliseconds easily, right? And so data lakes itself is slow to scan, and also your data files can be inoptimized for query performance, right? If it's not compacted correctly, they can be small files scattered, and that's horrible for scanning, right? For querying, for OLAP queries, right? And this whole fetching data problem has becoming even more severe with query engines now run so much faster, right? So the faster the query engine run, the less stress is on the CPU, the more stress is on the IO, right? So when query engine run faster, IO becomes more of a bottleneck, right? Even with really complex CPU intensive queries with, really large scale joins and high cardinality aggregations, right? That's supposed to be heavy on the CPU, but now on the IO because of these challenges. And also, getting fast queries is not enough, right? We still need to build ETL pipelines to further accelerate the queries, right? To do pre-computation, pre-aggregation, and denormalization, right? Just by storing the result of a query, right, as a separate table or field, right? And then query that to avoid on-the-fly computation, to avoid denormalization, to avoid on-the-fly joins, and pre-aggregations to avoid on-the-fly aggregations, right? Let's take an example here, right? Let's say you're using Spark to do that pre-computation job, and that's common, right? Let's say your data user identifies a slow query and it reports to you. You're the data engineer, right? And you add a pre-computation to your pipeline. That can be a denormalization pipeline that joins all of the tables and creates a flat table, right? That contains the result of the join, right? But that's not the end of it. It's not going to take effect until your SQL script is rewritten to point to the new denormalized flat table, right, for it to take effect. And that rewriting process is a big pain we see in the field. That forces the data engineers, to figure out all of the data pipelines, pre-computation pipelines prior to the data user or themselves developing the client-side application, right, SQL scripts, right? Because that's such a big pain, rewriting the SQL to point to the new table. Nobody wants to deal with it. So when they build the pipeline, they build a little more than they need. So that end up with generating pre-computed tables and pre-computation pipelines that never get used or very rarely get used, right? So a lot of waste of labor and computational power, a resource, right? And that this whole planning process significantly lengthened the development process, right? With a lot of experiments and understanding of your SQL and understanding of your data, right? And anticipating what the growth of the system is going to be, right? That takes a very long time. So you go to production a lot slower with the current ETL pipeline, pre-computation pipeline for query acceleration, right? And the reason for this is because query engines are running much faster now, right? And ETL pipelines are not really catching up with it. So before, query engines are fast, they were slow, right? A common practice we see in the field is that you have a Spark cluster that basically pre-aggregate and denormalize everything, right? And send the all of the pre-computed result to even a KV store or a transactional database that only does serving. So there is no like OLAP compute at query execution, right? So when you basically default to pre-computation to everything, this is not really big of a problem, right? But as query engines are running so much faster, people now have the option to do on-the-fly computation. But this ETL pipeline is not really suitable for that, right? And that's where we see the huge mismatch, right, of these two. So in the next section, we're going to talk about some methodologies of how to accelerate data lakehouse queries. So first, let's talk about raw query performance, right? Firstly, a cache is absolutely necessary for a query engine to have, right? Because fetching data, the process is very slow, right? And that first to overcome the unstable performance of data lake houses, right? And also to save IO cost from fetching the data, from external storage. So make sure that your queries is fast and stable, right? And second is that you want to look for those query engines that has MPP or has in-memory data shuffling, right? Older not query engine, processing engines such as Spark, right? When they do data shuffling, they basically persist all of the intermediate results to disk in order to be stable for a long running job, a very long running job, right? So let's say a job runs for 4 hours and it breaks at the third hour, so it can continue, right? It doesn't stop from the beginning. But that is good for huge long running workloads, but it's not really good for low latency workload, because anything that touches disk is going to be very slow, right? So you want to search for those query engine that runs completely in memory, thus optimize for low latency, high concurrency queries, right? And also you want to look for those query engines that has good system level optimizations. Specifically, you want to be written in C++, right? And the reason for that is to fully utilize the SIMD instruction sets, right? SIMD instruction sets basically say teaches the CPU, to run everything in batch, and in OLAP, everything is in batch. The more batch you run, the faster it goes. So C++ is absolutely necessary if you want to have the best of the best performance, right? And a lot of the query engines available today are really not optimized for pure query performance, right? They opt for a higher level language to develop, such as Java, which is faster to develop, but it really lacks in performance, right? Because before we didn't really have a lake house, and we weren't trying to unify all of the workloads on the lake, right? And before it was connecting to a million different data sources, right? And for that purpose, picking a language that's efficient in development is good. But now, if you want to run really high demanding workloads with that query engine, a C++ engine is absolutely favorable, right? Although Java, like JDK 21, they have a lot of optimizations for SIMD, or like auto SIMD, but it's nowhere near the amount of optimization we can do with the C++ engine, right? So these are some very high level points, but with the right tools, getting data warehouse performance on the data lake house is not only possible, it's actually quite easy to do, right? We're gonna talk about them. I'm gonna show some numbers in the following slides, right? So here, let's compare data warehouse to data lakehouse. And here I picked a query engine that's called StarRocks. StarRocks is an open source query engine, right? The reason I picked StarRocks is because it does both, and it does both really well. It can be a data warehouse where it persists the data, although in a remote storage, in the cloud object storage, but it's its own file format, right? With its own storage engine. So you can do like real-time analytics, right? So you can support real-time upserts, right? For real-time analytics, or you can swap the StarRocks storage engine out with the data lakehouse storage, right? You swap the SARS file format and the SARS table format out with Parquet files and, let's say, Apache Iceberg or Apache Hudi, right? So StarRocks can act like a open, like a high performance query engine for the open data lake, right? To get some reference point, let's first look at how fast is StarRocks as a data warehouse. So here is a benchmark of SSB benchmark. So the SSB benchmark basically resemble those multi-table but simpler queries like you would see in like reporting or a BI scenario, right? So there's one thing I want to clear out first. So you can see here you have flat and multi-table, right, on the right hand side. SSB originally is a multi-table test, but ClickHouse, the project, it creates a variant of the SSB benchmark test. So basically, you take all of the tables and perform a denormalization into a big flat table and only query the flat table, and basically remove all of the on-the-fly joins, but keep all of the on-the-fly aggregations, right? So on that variant of the benchmark, StarRocks is faster than ClickHouse and way faster than Apache Druid. And StarRocks on the original multi-table benchmark, SSB benchmark, is even faster than Druid's single table performance, right? And join is a very expensive thing to do. And this showcases like how fast StarRocks as a data warehouse is, right? So now we have a reference point. Let's do the comparison, right? StarRocks as a data warehouse versus StarRocks as a Lakehouse query engine. So this, to make it more difficult, this is the TPCDS 1 terabyte benchmark. So instead of simpler queries, so this resembles the queries of, let's say, ETL workload or and a more complex ad hoc query, right? So a lot of joins between large tables and also a lot of high cardinality aggregations, right? And this is run on the same exact hardware between StarRocks as a data warehouse and StarRocks as a query engine, right? And those are both hot queries. The data warehouse solution is only 12% faster, which means that you gain all of the benefits of a data lake house, unify all of your data in one place, keeping only one copy of the data, right? And not maintaining a billion different data warehouses, not have data scattered around, and only at a cost of 12% of the performance. And here's another comparison from StarRocks to another query engine called Trino. Trino is pretty fast, and this is on TPCDS, and StarRocks is 5.5 times faster than Trino on this, right? So this showcases basically just by querying, right? No pre-computation involved. It's completely possible to have data warehouse-like performance on the data lakehouse, right? So you can have those benefits of the data lakehouse while not really losing much performance. And then let's circle back to the ETL problem, right? To the ETL problem. There's one thing that has been going around in the industry is that a materialized view with full query rewrite, and this functionality can help you solve the on-demand pre-computation pipeline challenge we talked about before, right? A materialized view is basically a stored result of a query, right? And it's managed by the query engine itself. So a query rewrite is that when you write a query, it directly points to the materialized view, so you don't have to change your SQL script, right? With when you try to do pre-computation. So this solves the problem talk about with Spark, right? So the benefit is enormous, right? So you gain the flexibility of on-demand query acceleration, right? So you can default to querying the original table schema, right? And then use materialized views to fix those slow queries. And this gives you better user experience for data users because they don't really feel anything, right? Because they don't really need to change the SQL script, right? And that saves compute and storage from unnecessary pre-computation pipelines because you only build them when you need them, right? And ultimately, you go production a lot faster, right? And here's all of the theory talked about, but how does it look in production? And now we're gonna take a look at some Lakehouse architectures, actually from the StarRocks community. Actually, I put in the bonus one, the 6, for you guys that join today live. So the first one is Trip.com's Artnova platform. Trip.com is a leading travel company, and Artnova is kind of like an internal reporting platform, right? It's a huge company, and all of the reporting and dashboards is handled by this Artnova platform. So before they were on a classic Trino as a query engine, but not fast enough, have a data warehouse on the side to do acceleration kind of case, right? So StarRocks, they were using StarRocks as a data warehouse to handle all of the workloads that Trino cannot handle, right? So they basically ingest their data from their Hive into StarRocks for those workloads. Despite StarRocks ingestion is relatively fast, but there's still, it's still data freshness still takes a hit, right? And it also adds complexity to the data pipeline because they have to maintain this ingestion pipeline. They have many tables, and maintaining ingestion pipeline for that is not a simple task, right? And also they have to do a whole set of data warehouse data model design inside of StarRocks, right? Table schemas and index designs and a lot of things. And it's labor intensive, right? And just duplicating data to another data warehouse is complex, it's expensive, right? It's bad for governance, and it's expensive on the storage side. So they basically StarRocks took over, and they started using StarRocks as a unified query layer, right? So the immediate benefit is that it streamlines the architecture with one less system to maintain. And on the raw data, compare StarRocks to their previous query engine, Trino, they saw a 7.4 times performance gain on the same data, right? Not pre-computed same data, right? But they were doing what I was talking about with Materialized view. So they were doing that no ETL by default. So they query all of the raw data by default, and they only add pre-computation when they see a slow query, right? And ultimately, it only took 4 materialized views for them to solve all of their slow queries, right? So query rewrite capability ensures that there's absolutely nothing that the data user needs to do in terms of the SQL script. So the data engineer can handle this with a simple command, right? And this materialized view, the 4 materialized view combined with StarRocks performance, they saw an overall 10 times plus performance improvement when compared to Trino. And most importantly, there's no slow query anymore, so they don't need another data warehouse to do query acceleration, right? And the next one is ATRenew's data analytics on 100 terabytes of data per day. ATRenew is a global recycle company. So let's say you have an old phone, right? You can sell it to them, and and recoup some of that money back, right? And they're in the recycle business. They have enormous amount of data, so they have hundreds of terabytes of data per day, and for some of the tables, it stores up to 5 years of historical data, right? And then end up with 30 to 40,000 Hive tables in their Hive cluster, and the query often scan like half of the entire data set, right? They were trying to, they were thinking about an OLAP database or a data warehouse solution, right? But it was infeasible because the sheer amount of data they have is going to blow up the storage cost, right? So they end up with querying Hive directly with Trino, but the performance becomes an even larger issue, and that's just not able to satisfy their business requirement, right? Without blowing up the bank, adding too many nodes. So they transitioned to StarRocks. So on the benchmark, TBCDS shows that StarRocks has almost 16 times better performance than Trino when there's like 20 parallel queries, right? And when they deploy everything in production, 80% of the queries experience at least 2 times the performance gain. And the next case study is Tencent. Tencent is the gaming giant that has games like Honor of the Kings, PUBG Mobile, right? And this is their internal big analytics platform that does a lot of the the user behavior analytics, log analysis on those games just mentioned, right? Before they had a crazy, insanely complex system with many tools in it, right? So data was scattered between all kinds of places, and they had a separated real-time and batch analytics pipeline, um, like a Lambda architecture, right? So there are two pipelines for them to maintain at the same time, and that's costly, right? And also the pipelines are extremely long because everything needs to be pre-computed, right, on all of the data. That's including denormalization and pre-aggregation. They didn't like that, so they revamped their data architecture, right? So they unified all of their workloads and their data on top of one data lake house, right? And data can be ingested. So how it does is they have a real-time pipeline and a batch pipeline, right? So the real-time pipeline gets ingested into StarRocks storage engine first, and then periodically synced to Iceberg, to Apache Iceberg, right? To keep the single source of truth data on their object store, right? To complete the data lake house, right? And batch data is ingested into Iceberg, Apache Iceberg directly. And by doing this, they effectively lowering their storage cost by 15%. And that's a combination of, using object storage and eliminating a lot of the pre-aggregations and uh, denormalizations, right? And all of the pre-aggregations are eliminated because StarRocks is really good at performing aggregated queries, and as well as a lot of the denormalization pipelines, right? A simplified architecture means that they experience a 50% better efficiency when they add a new data pipeline, right? When they add something new, basically. The next is Tencent's ABetterChoice. That's a good name. Tencent's ABetterChoice A/B testing SaaS platform. So, um, Tencent is in the gaming business. They're one of the biggest in terms of revenue, the biggest gaming company in the world. And they have a really robust A/B testing framework, internal framework, right? And they try to so this is a story of them trying to transform that internal platform into a SaaS offering that's gonna help more gaming companies, right? The A/B testing, and that comes with a lot of challenges. So the first, the internal system is really data warehouse dependent. So it uses a lot of data warehouse for acceleration, right? And also it has limited support for join queries. So they had to do a lot of denormalization, right? And then going SaaS, right? So they have to handle a multi-cloud environment and needs to support multiple open lake formats, right? And the fourth challenge is from cost. So A/B test, A/B test collects a lot of data, a lot of user behavioral data, and that can blow up storage really fast. If they're doing for themselves, that's probably controllable, but serving that to external clients, other companies, and that cost can blow up really fast. Let's see how they address this issue. So the implementation is two parts, right? So first, they use the Tencent big data service internally, their big data cloud for their internal use case, and a Databricks based data lake house, right, on multiple clouds, including Azure, AWS, and Google Cloud. and they have a unified query layer that's based on StarRocks, right? And the result of that is a pretty simple architecture that both serve internal users and external customers, right? And also by unifying all of the queries with one query engine, right? SQL is unified, so their application can reuse a lot of the SQL script for their applications, right? And also StarRocks can do joins really well, so they significantly reduced the number of denormalizations they need to do when they compare to they were using a data warehouse internally, right? And also storage cost is reduced because less denormalization, and also cloud object storage is much more cost efficient. Sorry. The next use case is WeChat. WeChat is a social media platform that has 1.3 billion monthly active users. So before they were using a Hadoop-based data lake with a bunch of data warehouses for query acceleration. StarRocks is even one of them. And the requirement for their use case is it's insane. They have trillions of records per day ingested, and they want their P90 latency to be lower than 5 seconds, right? They were experiencing similar challenges than Tencent Games, just talk about, right? They also have a separated real-time and batch analytics pipeline, right? Managed system means they have to manage incompatible APIs from different systems, right? And also they have many data warehouses from each team, right, to do query acceleration. So maintain those ingestion pipelines for all of the data warehouses is a pain. And also data governance challenges from one data just get copied like in 15 different places. And ultimately challenges in standardizing their data analysis process, right? And also with a Hadoop-based data lake system, data freshness is really not good. It's in the hours. Let's take a look at their solution. So this is similar than the one with Tencent Games. They also has a real-time and batch pipeline, right? The real-time pipeline gets written into StarRocks and periodically gets synced into the object storage, which is managed by Apache Iceberg with Parquet files, right? And the batch data gets ingested into Apache Iceberg directly, right? And the result of this is they get, like, with trillions of daily records, they reduced data freshness from minutes to hours to seconds to minutes. So the real-time ingestion pipeline has a freshness of seconds, single-digit seconds, and their near real-time or their batch ingestion has latency in minutes, data freshness in minutes, right? And they also reduce 65% of their storage cost and shorten the development cycle for each task by 2 hours from simplifying their pipeline. And the last one I'm going to talk about is Red. Red is a social media company that has 200 million plus monthly active users. Their scale of data on Hive is insane. They have, I don't even know how to pronounce this, 1,000 petabytes plus of data, EBs of data, and that's in 10,000 plus Hive tables, right? And they were actually a long-time StarRocks user before they were using StarRocks as a query engine. So their ads business, advertisement business, customer facing, real-time customer facing uses StarRocks as a real-time data warehouse that receives 100 billion rows of data per day, ingestions per day, and they have 30,000 plus CPU cores in their cluster right now. And the average latency on that massive amount of data is 200 milliseconds, right? And before they were using Presto with their thousands of petabytes of data. the performance is not really good considering they're looking at their star cluster and see 200 milliseconds of latency, right? And also there are many technology stacks, right? They're maintaining StarRocks for the real-time purposes, and they have a query engine on the lake, right? And also they had some high availability concerns due to Presto's leader follower architecture, right? And then they kind of unified uh, the query layer with StarRocks. So the query see an average of 6 to 7 times the performance boost when it compares to Presto, and P90 latency decreased by 90%. So the query latency is not only faster, but is more stable, right? And also lowered operational costs because one less system for them uh, to maintain, and also with StarRocks, Trino, and Presto dialect support, the transitioning process was fast, right? Because the sequels are compatible. That's all I have for today. If you have any question, please post them in chat. I'll take a look. Is there somewhere I can read about the architectures you covered today? Yes. If you go to Seller Data's blog page, the first blog is the same title as this one, this webinar, five brilliant architectures, Lakehouse Architectures. There are links to all of the case studies that I covered today. These benchmarks is the test data result post somewhere. Yes. Except for the data warehouse versus data lakehouse one, we haven't published that yet. So today's webinar is the first time that it goes public. But all of the benchmarks are in both Seller Data website and also StarRocks site. Let's search for it. Can StarRocks query data store within itself while simultaneously querying a data lake? The answer is yes. You can even join. You can join the data that's persisted in StarRocks with data that's stored in external data lake house. Where can I get these slides? It will be available. If not, I'll send it to you. But it will be available. Could it support real-time fraud identification? For example, a suspicious transaction in an OLTP data source of StarRocks Lakehouse. Can this data be ingested into StarRocks layer in less than 500 milliseconds? So half a second. That's a little challenging for StarRocks to do, even with its own storage engine. So Star Storage Engine, we do data ingestion by mini batch. So that means 5 seconds and plus, we recommend. Right? If your data volume is very low, you can do lower. But half a second is going to put a lot of stress on StarRocks cluster. I recommend go ahead and test. Which one is better, query engine of StarRocks or processing logic in PySpark? Spark and StarRocks are not directly, they're comparable, but they're not the same thing. So StarRocks is focused on low latency queries. So even as a query engine, its sole purpose is to return the result as fast as possible, right? But Spark is built for processing, for batch processing. It can run a job for very long, like an ETL job for very long without uh, breaking, or even it breaks, you can continue the job, right? So the architecture is different and it's built for different purposes. That's all of the questions we have. Any more question? I'll give it 10 more seconds. So go take a look at the blog that's on Seller Data. That basically has everything I talk about today, as well as the case studies in a nice PDF format with more information. Oh, I haven't done the question. If it is used as a query engine to access OLTP data source and run query against the source, does what will be an impact on OLTP database? Um, Not really much. StarRocks, one way to get data streamed into StarRocks is through changelog, right? It reads the changelog of your OLTP database, and that should not be too much stress on your OLTP database. As long as the data freshness that StarRocks can provide satisfy uh, your requirement, I think it should be okay. The StarRocks have its own analytics tool. Um, StarRocks, the open source project, no, it doesn't really have. It's an engine, right? It can be a data warehouse or a data lake query engine, but some commercial variant, some commercial product that's based on StarRocks has this feature, right? Like for example, Seller Data Cloud. Not really analytics tool, but we have a good SQL editor, intelligent SQL editor. And also, if you want to use some like a BI tool, StarRocks is ANSI SQL compliant, so you can use it with basically all of the BI tools that's also ANSI SQL compliant. Like open source ones, Superset, it's a great one. Any more question? Okay, so if you have any more question, you can post them in a Slack channel using. Okay. If CTC is used to capture and load the data into StarRocks, what will be the latency? StarRocks storage engine, like I mentioned, can do 5 seconds and more stably. But really depends on your workload, the amount of data you have. Yes. Yes, it's MySQL compliant. Any more question? Okay, I think that's it. We reached 50 minutes. Thank you guys for joining. If I have more questions, please post them in the Slack channel or reach out to me on LinkedIn or the latest one. It should. Oh, I should make this public. Well, it should. If it doesn't, throw us the case. Um, um, in the forum, GitHub issue, or Slack, right? If it's not compatible, let us know. Okay, thank you guys for joining. See you guys next time.